Great. Now we're recording. Awesome. So just to catch everyone who's watching the recording up, we're talking about inverse trig functions. We have the f of theta equals sine theta as a function or any trig function. The input is the angle theta. The output is sine of theta. So for example, the input could be pi over 3. The output would be sine of pi over 3, which is the square root of 3 over 2. We would like a function that inverts this input-output relationship, meaning we want the new input to be what sine of theta is equal to. We're going to call that x. For example, in the one I just said, the new input would be the square root of 3 over 2. And we want the output to be the angle theta, which in that example would be pi over 3. Okay, so I'm just catching people up who are watching the recording. The name we give the function is f inverse of x. And in this particular case, it's called the inverse sine of x, and it's going to equal theta. So if sine of theta equals x, or if f of theta equals x, then inverse sine of x equals theta, or f inverse of x equals theta. So again, input is theta, output is x. The inverse inverts that. The input is now x, the output is now theta. They change places, they change roles. And as I'm about to, another name for the inverse sine of x is called the arc sine of x. And now here's why it's called the arc sine specifically. It has to do with the unit circle. So let me go back to that example there for a second. So here's the angle specifically pi over 3. And here's the point on the unit circle, which is the cosine of pi over 3, which is 1/2, and the sine of pi over 3, which is root 3 over 2. And we know that cosine of pi over 3 equals 1/2. And we know that sine of pi over 3 equals the square root of 3 over 2. And I'm going to write down a couple things that are also true. It is also true that the inverse cosine of 1/2 equals pi over 3. We're just flipping the relationship. And again, when I read this, I'm going to say this a few times. When I read this, I really think in my brain, the angle whose cosine equals 1/2. So actually, I should really kind of label that as just this part here. Right? This left-hand side, that part says the angle whose cosine is equal to 1/2. And I'm trying to find that angle. What's the angle? Oh, it's pi over 3. Or when I write down this, oops, not that. Sorry, when I write down this inverse sine of root 3 over 2, sorry, I'm kind of blowing it there. I really think of that, oh yeah, I'm looking for the angle whose sine equals root 3 over 2. And again, the answer is pi over 3. Now I'm going to stop any questions where you guys might be thinking, James, I know some other angles that if I took sine of that angle, I would get root 3 over 2. Like 2 pi over 3 would also be an angle where sine of it is equal to root 3 over 2. We'll get to that in a minute. Don't worry about that for now. But to answer the question is, why is it called the arc? Well, if I'm trying to find, again, and literally, you never have to think about this if you don't want to. It's the same thing. Arc sine and inverse sine, different notations for the same thing. But the reason why the arc sine is a notation we use is because you're trying to find the length of the arc. If you took sine of the angle subtended by that, you get the value. So here is the arc length. And if you take sine of the angle that goes with that arc length, you get that value, which is root 3 over 2. But here's what we know from the unit circle. From the unit circle, we know that the arc length and the angle in radians, that's why we like to use radians, these are the same. This is equal to pi over 3. So that's why it's called the arc sine or the arc cosine, is because literally you're saying, oh, if I give you this value, root 3 over 2, the value of some sine or cosine or whatever, we're asking the question then, what is the length of the arc it took to get to that point? So hopefully that clarifies it a little bit as to why you also call it the arc. And then one thing I want to stress is that this is not the same thing as 1 over sine. Right? Inverse sine is totally different. And this is not 1 over cosine of whatever. This is not 1 over sine of whatever. Right? That would be secant and cosecant respectively, which are totally, totally, totally different. So that's another good reason why people like to use this arc notation, because it makes it more obvious that we're not doing like the reciprocal of cosine, we're doing the inverse function of cosine, or inverse function, excuse me, of sine. Okay. Good questions. Sorry, someone was saying something?
Sorry.
That's okay. Did you have a question?
No, I just realized something. It's all good.
Okay, cool. All right, so that's the basic idea, is that if you know how to find sine of an angle equal to a value, or cosine of an angle equal to a value, or trig function of value equal to, or of angle equal to some value, you know how to find the inverse trig function of that value, and it's going to equal the angle. And the thing I really want to stress to all of you is that whenever you're finding an inverse trig function of some number, the answer you get should always be an angle. So for example, also, I'll show you guys something else cool I learned it. Are these only for ones on the unit circle? I mean, yes and no. So we're certainly going to show them for the ones in the unit circle, but technically you could find inverse sine and inverse cosine of any value that you could get on the unit circle. So I'll talk about that a little bit. So sine of pi over 6, we know is equal to 1/2, which means it's also true that the inverse sine of 1/2 is equal to pi over 6. Or as I would say, the angle whose sine is equal to 1/2 is, drum roll please, pi over 6. And I want to, again, really, really stress, it's literally saying the same thing as this, right? That's what this says. This says the angle that if I take sine of it, I get 1/2. That's what this says here. The angle whose sine is equal to 1/2. It's just we're reversing the order because we want a function where the input is the value and the output is the angle. Instead of using angles to find side lengths, we now use side lengths. Yes, excellent observation. That is exactly what we're doing. Instead of using angles to find side lengths, we are now using side lengths, or what I would really say values, but yes, to find angles. Because it's not, the problem is it's not always going to be in the triangle. For example, we know that sine of 3, oop, that's a bad example, James. We know that sine of 3 pi over 2, sorry, we know that sine of pi over 2, apologies, is equal to 1. And we also have that the inverse sine of 1 is pi over 2. Or if you prefer, the arc sine of 1 is pi over 2. Now, I do want to point out, you can't find the inverse trig function of a lot of numbers. For example, we cannot find the arc sine or the inverse sine of 2. If we think about the graph of sine for a minute from last class or the class before, we saw that the graph of sine looks like this. Oh, do I really want to draw that? Just now, I'm going to draw it again in a minute. I'll draw it again in a minute. I'll just say for now, we know that the graph of sine has a maximum value of 1 and a minimum value of -1. There is no angle where sine of that angle is equal to 2. So there can't be any answer to this because there is no angle where sine of that angle is equal to 2. Or another way of saying it is we would say that both of these are undefined. Let's see, there was something else I wanted to mention before I said that. Brain, where'd you go? I guess not. Okay, so there is something I alluded to just a moment ago, which is that there are other angles where sine of that angle is equal to, say, 1/2. For example, hopefully you all will agree with me, we also know that sine of 5 pi over 6 is equal to 1/2. That is also true. Right? We definitely, right, it's in quadrant 2, sine is positive, the reference angle is pi over 6, you get the same y value. Or you could even look on the unit circle if you want to be like, oh yeah, James, I know that, pi over 6 lives right there. And the point there is 1/2 comma root 3 over 2. And 5 pi over 6 lives right there with a reference angle of pi over 6. And that point is negative 1/2 comma, sorry, I got those backwards. Negative root 3 over 2 comma 1/2. And that's positive. Sorry, and it's getting a little messy, I apologize. The point is that both pi over 6 and 5 pi over 6 have the same sine value. But here's the thing. We don't want but the inverse sine of 1/2 is not equal to 5 pi over 6. We already know what the inverse sine of 1/2 is equal to. It's equal to pi over 6. What I'm kind of talking about here, what I'm definitely talking about here, is the fact that we want the inverse sine function and the inverse cosine function and any inverse trigonometric function to actually be a function. Meaning that when we have one input, you only get one output. So if my function is the inverse sine of x, I want to be able to input the value of 1/2 and not get two different outputs out, right? That would be a big problem for not being a function. It's exactly like the square root of x function. Technically, well, I don't want to say technically here. If I was asking about what number squared was equal to 9, there would be two answers. 3 squared equals 9 and -3 quantity squared equals 9. But this function, and it is a function, if I ask you what the square root of 9 is, there's only one answer. The square root of 9 is +3, right? This isn't a plus or minus square root. We put a plus or minus on there when we want to find multiple solutions. But if you're taking the square root of something, you're only getting the positive answers out. Because just like the inverse sine function, we want the square root of x to actually literally be a function. Meaning if you put in one thing, you get out one thing only, not two different things. I don't want to put in 9 here and get 3 or -3. I don't want to put in 1/2 here and get pi over 6 or 5 pi over 6. So what do? Well, this is where things get a little bit interesting. So I'm going to draw this stuff, but I'm also going to show you it does this. So f of theta equal to sine of theta is not what we call a one-to-one function. It's not a one-to-one function. If you graph it, draw the graph real quick. 1 minus 1. So if we graph it, it looks like this. It looks like that. So here's theta, here's f of theta. And the problem is, right, if you draw a horizontal line, it'll cross through multiple points. That's what it means to not be one-to-one. So not a one-to-one function means it fails what we call the horizontal line test. It's like the vertical line test, but horizontal. So why does that matter? Well, when you're finding an inverse function, you literally invert x and y, right? The y's become x's, the x. If any of you have ever found inverse functions before, the process usually is to interchange x and y and then solve for y. But when you interchange x and y, I know it's going to sound like I'm repeating myself. You interchange x and y, meaning the x-axis kind of becomes the y-axis and the y-axis kind of becomes the x-axis. So if instead I was going to graph x equal to sine of y, so right, instead of, and I know I'm using slightly different notations here, and there's kind of a reason for it. So instead of y equals sine of x, we're going to look at x equal to sine of y. And so that's going to end up doing this thing. All I'm really going to do is I'm going to interchange my xy coordinates for each point. So instead of 0, 0, I get 0, 0. And instead of the point pi over 2, comma 1, I get the point 1, comma pi over 2. And instead of the point pi, comma 0, I get 0, comma pi. And instead of the point 3 pi over 2, comma negative 1, I get the point negative 1, comma 3 pi over 2. And instead of the point negative pi over 2, comma negative 1, I get negative 1, negative pi over 2. Sorry, that point's right there. And here's what it looks like. Whoops. Oh, come on, you can do it. Yeah, okay. Or if you want nicer graphs, you can just look at this. So I've already gotten them all kind of laid out. Here's y equals sine of x, as is usual. And here's x equals sine of y, the inverse relationship. And what I want everyone to see about x equals sine of y, and I think you already know this, is it's not a function. It fails the vertical line test. That's a problem. We want it to be a function. So what do? Well, what we do is we restrict the domain. Actually, what I should say is we restrict the domain of this, like this. Sorry. I always do that when I'm doing a fraction. I forget to like do that. So look, if I look at this thing now, this restricted domain thing, it is 1-to-1. It passes the horizontal line test. Any horizontal line I could draw would only go through one point. And if I do the same thing for this, if I restrict the domain here, I end up with, instead of this, I get that. And that green thing, that is my inverse sine function. And notice, right, there's not a lot of it. It's the inverse of this, and there's not a lot of that. Good question here. I'm sorry. I mean, yeah, good question. So what does the horizontal line and vertical line test do? And what I'll say is they don't really do anything, but they tell us things. So sorry, let me go back to my notes here. So the horizontal line test tells us if a function is 1-to-1 or not. I'm going to tell you about that too, Faith. Excellent question. How do you know where to put the restrictions? So good. And I'll get there in just a second. So if a function fails the horizontal line test, it's not 1-to-1. If a function fails the vertical, sorry, if a graph fails the vertical line test, it's not a function. And here's the connection between the two. If a function fails the horizontal line test, its inverse relationship will have to fail the vertical line test. Or failing the horizontal line test means its inverse won't be a function. And so what we do to make it so it will be a function is we restrict the domain. We say, well, I'm going to restrict this to a piece where it's going to be 1-to-1, which is just from here to here. Just that little bit right there. So here is sine of x restricted to x being between negative pi over 2 and pi over 2. Faith has asked an excellent question. How do we know where to put it? And the answer is mathematicians mostly all agree on where to put them, but we kind of all just decided at one point. So the way I think people decided, and I don't actually know how they decided, but I know what they are, is that typically we want to include the first quadrant if we can. So we always want to include everything from 0 to pi over 2. And then if we can, in my opinion, and there's other people that disagree, I guess, if we can, we want to also include the quadrant that is next to it that will make it 1 to 1. So I can't include this quadrant here because if I did the quadrant from pi over 2 to pi, which is the second quadrant, I wouldn't pass the horizontal line test anymore. But if I include this quadrant here, which is the negative pi over 2 to 0, which is the fourth quadrant, that will be the part where it's the 1 to 1. So, and I will definitely talk about where all the restrictions go as we go along, but that's kind of the idea. And so then the inverse, instead of x equal to sine of y, we're going to instead say, well, we're going to do with the restriction, we're going to get y equal to inverse sine of x. We're going to get this lovely looking graph. So it looks like that. Okay, so here is the takeaway from all of this. If you're evaluating inverse sine of x, so y equals inverse sine of x, the domain, which isn't super important, but I'll just point out the domain is negative 1 to 1, right? Which I kind of already talked about, right? You can't take the inverse sine of 2 because 2 is outside of the domain of the inverse sine function. But more importantly, the range, which is the range of outputs we're allowed to get, the range is as low as negative pi over 2 and as high as positive pi over 2. So when you are asked what the inverse sine of a value is, your angle should be something in the first quadrant or something in the fourth quadrant, but not, and so here's what's kind of confusing about it. You don't go counterclockwise all the way around to quadrant 4. You instead go just back a little bit to quadrant 4. You get a negative answer. Let me show you some examples. So, for example, we already talked about, God, my paper gets all like dotted up here. I guess it's not a big deal, but I can use the other side. Okay, so we already mentioned that the inverse sine of 1/2 is pi over 6. Because sine of pi over 6 is equal to 1/2. The inverse sine of negative 1/2. So now I'm looking for an angle whose sine is equal to negative 1/2. There are literally an infinite number of choices for an angle whose sine is equal to negative 1/2. There's 7 pi over 6, there's 11 pi over 6, there's other things, but the answer we are looking for is negative pi over 6. And the nice thing about sine, I should say, the nice thing about inverse sine is that it's really straightforward. If you know that the inverse sine of a positive number is some positive angle, then it is always going to be true that the inverse sine of the corresponding negative number is the corresponding negative angle. Think about the graph, or the unit circle, I should say. Right? If that angle right there is pi over 6, and we know that the sine value is 1/2, then we know that if we go pi over 6 down, so that's negative pi over 6, right? Because we're going clockwise, which is the negative angle direction. The coordinate here is going to be the same x coordinate, but the negative y coordinate. So that value there is sine of pi over 6, and that value there is sine of negative pi over 6. And so I think it's not too terrible to see that, oh yeah, this means that the inverse sine of 1/2 is pi over 6, and the inverse sine of -1/2 is -5/6. And that's always going to be true for the inverse sine function. And also for inverse tangent, but not for inverse cosine. Inverse cosine is kind of weird in that way, but it works great for inverse sine. So for example, I could also ask, I could also say, I know the inverse sine of the square root of 3/2 is pi/3. I will also mention you could use degrees if you wanted to. I would prefer you use radians, but it is technically perfectly correct to use degrees as well. Just make sure you use the degree symbol if you do it. Also, fun fact, I learned how to find the inverse sine function on my phone today. I was like, how does my phone not have the inverse sine function? So just so everybody knows it, if you're looking at if this is the calculator you're using, and let's say we're in radians, I wonder what will happen. So, we can do sine of, oops, I always forget this is backwards kind of, right? We can do pi, where's pi? Pi divided by 6 equals, and then we can take sine of that, and you get 0.5. And if you want to do the inverse sine of 0.5, you have to go to, let me clear this here, the second, and that's where your inverse trig functions are. And so if I wanted to do like 0.5 and then do the inverse sine of that, it's not going to give me a very nice number because my calculator is in radians. But if I changed it to degrees, then I could do, let's try it again, 0.5, the inverse sine of that. Oh, it's 30 degrees or pi/6 radians. So that's how you can use your phone calculator, if this is the phone calculator you have, to find inverse trig functions. Again, I won't usually be asking you to find inverse trig functions of anything you need a calculator for anyway. But just to go back to a previous question that someone asked, which was, what was the question? Someone asked, are these only for ones of the unit circle? You could totally find the inverse sine of, say, like 4/5. But I don't know what that is. There is some angle that if you took sine of that angle, it would be 4/5. But you would need to use the calculator. The point I was trying to get to, I know there's a lot of things going on here, is that if we know this, then we kind of automatically also know that the inverse sine of -√3/2 is equal to -pi/3. Or as I would phrase it, the angle whose sine is equal to -√3/2 is the angle -pi/3. And again, I know there are lots of angles that is actually true for, but the inverse sine function specifically is defined to have angle output values that are between -pi/2 and pi/2. Why? Because a bunch of old mathematicians agree that that's what it should be. There's really not a great reason other than it's kind of, I mean, it is good because it's like got the first quadrant. I think that's nice, but really like you could have picked 2 totally different quadrants and had everything work out just as well. So it is kind of an arbitrary choice that some people made a long time ago, and we're kind of stuck with it now. Which I know is not the best answer ever, but it is kind of the real answer. Okay, so how much time have we got? Yeah, I'm just really burning through time here. So let's go ahead and do that. Yeah. Cosine, similar, but a little different. Since I'm kind of strapped for time, I'm going to show you these graphs, not by graphing them, but by showing you on Desmos, because I want to get to the point. So let me share before I forget to do that. New share, screen. So close these, close those. Great, move that out of the way, great. So here is good old cosine. And here is the inverse relationship, x equal to cosine of y. And as you can see, oh yeah, that's definitely not a function. But if we restrict the domain of cosine to, let me just be smart and, well, actually, so here's the thing is I actually don't want the same domain restriction here. Let me show you why. If I do that, that is not a one-to-one portion of cosine. Yeah, exactly. It's the same graph, just vertical. Exactly. We're just interchanging x and y. Another way to think about it, right? the red graph versus the black graph is they're actually reflections of each other in the line y equals x. Those have symmetry about that line. If you take that red graph and flip it across the blue line, it'll look like the black graph and vice versa. But what I wanted to say is we don't want this domain restriction because that portion of the cosine graph is not one-to-one. It totally fails the horizontal line test, right? There's a horizontal line that goes through more than one point on the black graph. But if we do this domain restriction instead, and technically it should be, sorry, I'm making a small error here. It should be less than or equal to, and it should be less than or equal to, right? If we do this domain restriction, oh yeah, look, that graph is totally one-to-one. It definitely passes the horizontal line test. And the inverse of it, which instead of this whole entire red graph is just this blue portion of the red graph. That is the inverse cosine function. And let me say some things about that. So I'm going to stop. I'm going to share my other screen again. So y equal to the inverse cosine of x, or y equal to the arc cosine of x, looks like this. And again, I really think of, right, usually the cosine graph would have the point 1, or sorry, 0, 1. So this one has the point 1, 0. And the cosine graph would usually have the point pi over 2 comma 0. This one has the point 0 comma pi over 2. And instead of pi comma -1, we're going to have the point -1 pi. So the inverse cosine graph looks like this. And again, that is literally the entirety of the function. That's it. That is all of the graph there is. The domain is still the same from -1 to 1. So you can't take the inverse cosine of 3 or -3 or anything outside of this. And the range is 0 to pi. So when I ask you to find the inverse cosine of a number, your angle should always be something between 0 and pi, or between 0 degrees and 180 degrees, or somewhere in quadrant 1 or quadrant 2. So, for example, if I wanted to find, say, the inverse cosine of positive 1/2, that would be equal to pi over 3, because we know that cosine of pi over 3 is equal to 1/2. But if we wanted to find, say, the inverse cosine of -1/2, well, again, I'm going to remind you, this says the angle, I'm going to leave some space here to add something in. The angle whose cosine is equal to -1/2. But the thing I'm leaving out here is that it's the angle between 0 and pi radians. And right, the same thing back here, right? This here was really the angle between -pi/2 and pi/2 radians, whose sine is equal to -1/2. So now that we have that restriction, we're like, oh, well, it's got to be, it can't be quadrant 1 because cosine is positive in quadrant 1. So it's got to be in quadrant 2 because quadrant 2 is where cosine is negative, or one of the places where cosine is negative. So the nice thing is we pretty much know the answer already. We know that these values have to have the same reference angle. So we know the angle, or the reference angle, is pi over 3. We're just looking for the angle in quadrant 2, whose reference angle is pi over 3. That's 2 pi over 3. Right? If you know cosine of pi over 3 is 1/2, you definitely know that cosine of 2 pi over 3 which is in quadrant 2, is equal to -1/2. In a similar way, I could point out that we know that the inverse cosine of √2/2 is pi/4. Right? The angle that if you take cosine of it, you get √2/2 is pi/4. So I'm going to ask all you guys and girls, the inverse cosine of -√2. I try not to say guys so much, but I just can't help it. It's just part of my vocabulary. I'm trying to break. So the inverse cosine of -√2/2 should be something over 4. How much pi/4 should I have? I can't even see the chat. You guys could all be typing, like, James, we're saying things. I know you know. I know you still want to say you know. I know you all know it's 3 pi/4. Because it's got to have the same reference angle because it's essentially the same value, just negative. Or inverse cosine of √3/2 is pi/6 because the angle that if you took cosine of that angle to get √3/2, the angle would be pi/6. And so we know inverse cosine of -√3/2, or as I like to say, the angle whose cosine is equal to -√3/2. Same reference angle, quadrant 2. Yeah. So tangent is similar to cosine. Oh my God. Erase that from your memory. Tangent is similar to sine in that tangent and sine have the same range, essentially, with a tiny, tiny difference. So I know we didn't talk about the graph of tangent. So let me just say a few things here. So tangent is similar to sine. What do I mean by that? Well, y equal to inverse sine of x has a range of -pi/2 to pi/2. And y equal to the inverse tangent of x has a range of -pi/2 to pi/2. Essentially the same, except that you don't actually get the endpoints. And the reason why is because, and I feel like you guys will agree with me, we have seen that tangent of pi/2 is undefined. So you can't take the inverse tangent of some number and have it equal to the angle pi/2 because you can't take tangent of pi/2 in the first place. But other than that, it's essentially the same idea. If I wanted to find the inverse tangent of, say, I don't know, pi/4, that would equal +1. Because we know that tangent, oh, wow, whoa, wow. And my brain is just, please don't write that down. I feel guilty even having said it. So let me make myself feel better and scratch that out. Wow, tangent of pi/4 equals +1. But let me just unbrain that there. Sorry about that. Let me try again. The inverse tangent of +1 is equal to the angle whose tangent would be +1, which is pi/4. And that is because tangent of pi/4 is equal to +1. In a similar way, we could say that the inverse tangent of -1 is equal to -pi/4 because tangent of -pi/4 is equal to -1. -pi/4 is in quadrant 4, so we get that tangent of -pi/4 is equal to -1 because tangent is negative in quadrant 4. Something I want to say about this is a mistake I often see with this kind of stuff is I will see people definitely say, oh, inverse tangent of -1. I've seen, this is not right. I'm gonna write a not equal sign in a second. I've seen people write this before. And it's equal to 7 pi over 4. Unfortunately, that is not correct. I totally understand why someone would want to say that, because 7 pi over 4 is that angle there. But unfortunately, that's a too big number. We're looking for this angle here, which is negative pi over 4. I recognize, and I'm sure you recognize too, that they are coterminal, right? That they end at the same place. But 7 pi over 4 is really big. Like if you actually found the number, 7 times pi divided by 4 is like bigger than 5. And that's way outside the range of the inverse tangent function. So just be careful, right? If you're getting an answer in quadrant 4, it needs to be a negative angle number. So another way you could say this, and I know this is kind of weird, is almost out of time. Okay. So another example would be like the inverse tangent of the square root of 3. So again, we're looking for the angle that if you take tangent of it, you get square root of 3. That's going to be pi over 3. But it would be okay to say that the inverse tangent of root 3 is 60 degrees. Again, I would encourage you all to use radians, but it is not incorrect to use degrees. And then I will also mention the inverse tangent of negative root 3 is going to be negative pi over 3, or negative 60 degrees. It just means you're going clockwise instead of going counterclockwise. I do want to show you, so I don't think it's a good idea to start the more complicated expressions with the inverse trig. I think we'll save that for tomorrow because today is Tuesday, right? Today is Tuesday? Today's Tuesday, yeah. Tomorrow is Wednesday. Homework is due on Thursday, right? Right? Yes. So we'll have time to get to the stuff that will be on the homework that's due Thursday tomorrow as well. So that said, there are notes you can look at if you want to get a jump start on what is still on the homework. We will definitely finish these more complicated expressions where you take sine of inverse cosine of something or something like that. We will do that tomorrow for sure, and then we'll also do the notes from tomorrow. But I want to say in this last minute is I do want to show you the tangent graph just so you can have seen it. So let me share. Wow. Okay. Yeah. So excellent question. So there is a midterm that is coming up that is going to be due. So the due date for it is going to be Saturday evening, but you can turn it in late if you need to. Yeah, I was going to talk about that tomorrow. But yeah, there will be a midterm this weekend. There's a practice midterm already up on Canvas if you want to take a look at it. It will be very similar to the actual midterm. I feel like that answers enough of your question for now to answer the midterm question. But yeah, definitely, yeah, we do have a midterm this weekend. It'll be available after class on Thursday. And then it will be due, the due date for it is, I think, Saturday at 11 p.m. But I think the late due date is like Sunday at 11 p.m. So, and really, it's okay if it's late. I would prefer you turn it in at the due date, but if you turn it in late, there's no penalty for that. So no worries. Again, as with the quizzes, if you have any issues, any concerns, you can always get a hold of me. Send me an email, send me a message in Canvas, whatever. Yeah, good question. Definitely good to be looking out for what's coming up.
I have a quick question about the midterm. Because it says midterm exam for real.
Yeah.
And so
yeah.
that's the practice one?
Oh, does it say that on the practice?
It's available already.
Well, but so let me ask you, when you go click on it, can you actually get to the actual PDF in Gradescope?
It says it looks pretty open. It's just a submission and rubric, but I'm not sure if it's like.
But can you actually see
I don't see it on Gradescope though. I don't think I see it on Gradescope yet.
Right. So yeah, I did make it open so that you could actually see all the information. So like
Got
if you go to assignments or if you go to modules, let's go to modules. So if you go to modules and scroll down to the practice midterm. Right, so here's the practice midterm that had a mistake on it. Here's the actual practice midterm that you should look at. Here are the solutions to it. And then here is the class recording from when I did the midterm for. And then yes, here is the midterm exam for real. The reason I did that is because I was having a trouble making something linked before, so I changed the name of it. And like I was having an issue, so I changed things. But here's all the instructions. Here's the stuff you should know before starting the midterm. And then if you go down here, it should load it. And now, when you load it, you shouldn't be able to see it yet. Now I can see it if I go to edit the outline. That said, I forget how you see the thing, to be perfectly honest. Let me check my settings. I don't know exactly how many questions there. I'd have to go look. But the settings, let's see, let's make sure. Allow students to view and download the template. Yeah, so once it is available to you on Gradescope, you should actually be able to see the midterm exam and download it. Just like you have been able to do with the quizzes, right? I'm not hearing any yeses there.
I'm gonna double check Gradescope right now just to
Okay.
see what pops up on there.
But yes, you shouldn't be able to access the exam yet.
Okay. No, yeah, it's not on there yet.
Cool, good, yeah, that's how it should be. So it'll become available on Thursday right after class. And then words, James, I'm sorry. And then, yeah, you should be able to access it just like you have with the quizzes. Number of questions, I don't remember exactly. I'll take a look at that and see. I will say that the number is probably slightly misleading because I'm sure some of them have sub questions, so I'll try and be more precise. But back to what I was doing before is, let me talk about tangent for just, I know it's past time, but let me talk about tangent for just a minute. There's the graph of tangent. It's kind of funky. As you can see, just like with sine and cosine, it fails the horizontal line test. Any horizontal line you draw would definitely pass through multiple points, literally an infinite number. But if you restrict the domain here, you get one nice little section where it is passing the horizontal line test. And then if you do the inverse relationship, whew, that's crazy looking. But if you just do the inverse function with the restricted one, there's your inverse tangent function. And you can see, hopefully, that the inverse tangent function has an output that is between pi over 2. Why aren't you graphing that for me? Oh, because I'm not turning it on. And negative pi over 2. The inverse tangent function definitely has outputs between negative pi over 2 and pi over 2. I don't think we really need to know how to graph this just yet. It's not super hard, just that it's not, right? We have only so much time. But what I want to say is that it is just like the inverse sine function. The inverse tangent function has values that are between negative pi over 2 and pi over 2. And hopefully seeing that graph helps you observe that a little bit. So if I had to draw the things, right, I would say, oh yeah, look, here's one period of tangent. And here is the inverse tangent. The vertical asymptote here becomes a horizontal asymptote here. And just to say one more thing, you can think of tangent as sine over cosine. So at 0, you get 0 over 1, which is 0. And then as you get closer and closer to pi over 2, the sine value gets closer and closer to 1, and the cosine value gets closer and closer to 0. So as the x values move closer and closer and closer and closer and closer to pi over 2, this fraction gets really large, which is why you have the vertical asymptote there. Okay, I've said more than enough. I should stop, even though I didn't get through everything. But tomorrow we'll get through the rest of them. And yeah, I'll stick around. You're free to go. I have office hours at 3. you're welcome to come then. You're welcome to stick around from now until then if you want to and ask questions about anything. I'll be here, but you're welcome to go. So go if you want, stick around and ask questions if you want as well.
Hi, I just wanted to make a note that like on my homework that I turned in yesterday, that was it today, I like did the work for 2A on